Okay, so first I would like to thank organizer for the kind invitation. So very happy to be this nice center. So today we will talk about something about p-adic theory, which is, at this moment not directly related to b-adic conjecture, but from yesterday, Professor Dameng's talk, we see that the p-adic techniques, plays an important role in this b-adic conjectures. Hopefully, this will have some. Will be helpful in the future. Okay, so I will start with some background. Okay, so p-adic Hodge theory is somehow the p-adic analog, motivated by the complex Hodge theory. So in complex Hodge theory, okay, so we have the deRham comparison theorem, so everybody know that. And I would like to formulate this comparison in the following way so that we can adapt it to the p-adic case. So suppose X over R is a proper smooth variety. Okay, then we have the comparison between the Beatty side. Okay, the C points of X with real coefficients and tensor over C. And isomorphic to deRham side is a deRham cohomology. Are coefficients and the base change to C. And also, this isomorphism is equivalent with respect to the Galois action, Galois C over R. Okay, so in a complex case, the Galois group is easy, but in the p-adic case, the situation becomes a little more complicated. Okay, so inspired by this complex Hodge theory, this is a deRham comparison. The goal of the p-adic Hodge theory is like this. So we start with, for example, a proper smooth variety over QP. So algebraic variety. And the goal is to find certain the ring of, we call it ring of p-adic theories. Okay, ring of p-adic theories. Okay, which is satisfy, we call B, and such that satisfy the expected condition that we have a cohomology of X bar tensor over this B isomorphic to deRham cohomology of X. Also base change to. Because this moment is over QP, so and also with respect to the Galois action. Okay, then the first naive idea, inspired by this complex Hodge theory, the first naive idea may be to take. First, so naive idea. Because, okay, so this is a picture I really would like to draw in every of my talk, is that you have a rational number Q, which is the central object of number theory. They will take various completions. You have the Archimedean completion and also this non-Archimedean completion. Okay, then you take algebraic closure. You get complex numbers in Archimedean side. Then you take an algebraic closure in the p-adic side. However, this is finite extension. This is infinite extensions. I don't understand why. So this is not complete. Then to have good property, you take completion. I'll see. Okay, so maybe the first naive idea is just to take B equal to CP. This doesn't work. The reason is that not work. If you take the H0 Okay. For simplicity, I use GQP to denote a Galois group of QP. So CP1, you twist it at a second atomic character, which is equal to 0. Okay? So, but in the comparison, okay, this CP, okay, okay, QP, yeah, CP1, yes. And because QP1 already is naturally in geometry, so if you have this, plug this into this comparison, you will have that right-hand side is somehow non-trivial things, but left-hand side is trivial things. Okay, so this is a contradiction. Okay, then maybe I think this is essentially due to Tate. Okay, and because this is the abstraction, so maybe we just take all of this into account. There had to be Hodge-Tate, which is defined to be of CPI. Okay, so this is a gridded ring. This means that when you do this multiplication, you have CPI. Use the CPI tensor with CPJ, canonical isomorphic to CPI plus J. Okay, and it works in some sense. So then you have the Falting's conversion, Hodge-Tate conversion theorem. Falting's through this Hodge-Tate comparison. Okay, so left-hand side again, this is a tall tensor. Okay, this X bar QP, so tensor with this B Hodge-Tate. But right-hand side is not deRham cohomology. This is like a gridded piece of this deRham cohomology. Somebody call this Hodge-Tate cohomology. So, Hi minus J. So X omega X J. Okay, tensor B Hodge-Tate. Okay. Okay. Then we come to the third idea, Fontaine. Yeah, due to Fontaine. So the idea is to, okay, we now construct something which we call BDR, because we have this comparison, Hodge-Tate comparison, and this is the gridded piece. The gridded pieces of the deRham cohomology, because deRham cohomology has filtration, right? You can take this gridded module. So we expect this ring has a property that first, of course, you have a GQP action on it, and also we have a filtration. Okay, so with exhaustive filtration. Few, yeah. So such that so BDR is isomorphic to B Hodge-Tate. Okay, yeah. So in fact, this is somehow, finally, this ring is actually a complete discrete value field, okay, and or QP. So in fact, you can embed QP bar into this ring. This is very important. We will see later why this is important. Sorry? This is, sorry, yes, right. Okay. Okay. Yeah, Galois equivalent, yes. I feel like, I say Galois equivalent. Yeah, and it has some other, nice properties which I don't have time to say more explicitly. Then, okay, you can define, we give the definition of deRham representation. So a p-adic representation, say V of so GK. So here K is a finite extension of QP. Okay? It's called deRham. If this DDRV, which is defined to be V tensor with the BDR, okay, and GK around has the same dimension okay. This is actually a vector space over K. Okay, so this is vector space over K. The same dimension over K as the dimension of V over QB. Okay, so in general, this the general fact is that this dimension is always less than or equal to. But when the equality holds, we call this deRham representation. And we have the Faltings, and Faltings prove that this is actually the right object we expect. So that is, we really have this deRham comparison. Okay, so in particular, you know that this is a talk homology. This is okay. This carries a Galois X. This is deRham representation, and the DDR of this the talk homology equal to just equally to this deRham homology. Okay, so this is from a geometric point of view. Then why arithmetic geometry concern this deRham representation? So this is the importance we can see from this famous Fontaine-Mazur conjecture. Okay. So suppose we have a global p-adic representation. A global p-adic representation, which is geometric. Okay, geometric, in a sense, Fontaine-Mazur just means ramified at almost all places plus deRham at P. Okay, yeah, these two properties called. I mean, sometimes if in some papers they also added the condition that irreducible, but in that case it corresponds to classical things. And I think the original version of the conjecture has no condition on this irreducibility. Okay, then then the conclusion is that rho comes from geometry. Okay, in particular, when the dimension equal to 2, we have more precise prediction about where rho comes from. In fact, it comes from a twist of modular forms. So you see this deRham things really plays an important role in number theory. For long as the program. Okay. Yes. Yeah, this is somehow, you have the Tanaka formalism for, yeah. Sorry? No, not necessary, because I think there's a recent result of Frank Caligari. He proved that there's no even color representation. Okay. Yeah, in other papers, they put the condition odd, but now it's not necessary. Okay, so now let me state the results of this work. Okay, so this part is joined with Xinwen-Zhu. So again, the fixed notation as before, so K is a finite extension QP, but now X is we come to rigid world. So this is X is connected, rigid, analytic world. Okay, and L is a local system, QP local system. On a tall set of X. Okay, then the result is, the first result, we call this rigidity, so deRham rigidity. Suppose, so if this is a local system, I mean, it's deRham at one point, because at one point, you specialize this local system, you actually get a representation, okay, at this point. And then the Galois group of this, I mean, the residual field is finite extension of K, so okay, so you get a p-adic representation. So this, if Lx naught is deRham at some x naught, x, then it is deRham everywhere. For any x in x. And also, all those this deRham representations has the same set of Hodge-Tate weights. And the Hodge-Tate weights of Lx, okay, as a set counting with multiplicity, it's just the same as the Hodge-Tate weights of Lx naught. So moreover, if X is if X is smooth, then we can even talk about the deRhamness for local system. So in this case, then L itself is a so-called deRham local system. It's deRham local system. So in the sense of Schwarz. Sorry? What do you mean? I will explain this later, yeah. Okay, so then we have a more global conclusion, maybe corollary. I mean, concerning this Fontaine-Mazur conjecture. So this case, we assume that X is connected algebra variety. Okay, so over a number field. Number field. So L is as before, is a tall QP local system. Then if Lx naught is geometric, for some close point, Not. Yes, yeah. This is local system on the Etoile set of X, right? Okay, yeah. Yeah, yeah. In this case, we take a rigid analytic, but now we go back to algebra variety. Okay, yeah. Yeah, because in the proof we use this Nagata-Zariski purity, which is only for variety, for scheme. Yeah. Then Lx is geometric for any closed point. Okay, yeah, in the proof we basically just this theorem plus this purity theorem. Yeah, geometric, I mean, defined it here. No, I mean, yeah, subquotient, yes. Yeah, come from geometry means, I mean, the subquotient of the homology of some algebraic or number field. Okay, so the definition of geometric is purely representation theoretical. And conjecture is that if this has this geometric property, which is, I mean, purely representation theoretical, then it should come from geometry. Okay? And here we only take the representation theoretical part. Yeah. Oh, sorry. Okay, then we have a natural application to Shimura varieties. So this is Shimura data. Then you have a sufficiently small level, which is neat. Okay, then you have this Shimura variety over a number field, this canonical model, is over a reflex field, field E. V is a pure rational representation of G. Okay, so under some mild condition, we can associate a tall QP local system. Because LV on the Shimura variety. Okay, then the result is so this LV is everywhere geometric. Any closed point X. Yeah, so a priori, I mean, before, previously we know, I mean, this result for example, abelian type Shimura. So once you have a modular interpretation, you can use comparison to conclude. But now, for general, for example, for exceptional group, I mean, you don't have the modular interpretation for Shimura variety, then this result is new. Okay, so now I'll come to the technical part of this work. Before that, let me see. Okay, good. Yes, I think for abelian type, I mean, basically you know this. Yeah. Okay. Oh, I should say that I'm not sure the geometrical part if you know or not, but for deRham, you know the representation of deRham, that's okay, yeah. But for geometric, I'm not sure people know it or not. Yeah, because you have model interpretation, you can use the deRham comparison too. Yeah. So we have this so-called p-adic. We formulate a p-adic arithmetic. Riemann-Hilbert correspondence. Okay, so now I'll explain to you what does a deRham local system mean. Okay, so Fontaine has this construction of deRham pillar ring and deRham representation. And of course, if we want to generalize to a relative situation, namely you consider the local systems over algebraic varieties or originality varieties. So you need to first globalize the construction, or maybe shiftify the construction of this deRham pillar ring. Yeah. Then to do that, so globalization of the pillar rings. Yeah, for this, the basic Tor, the key Tor is the so-called perfectoid spaces and projectile side, okay, which is introduced by Schultz a few years ago. So I don't have much time to say the detail about this perfectoid spaces and projectile side, but just give one, I think, key examples. So you have this torus, for example, let's just say one-dimension torus. So in the analytical world, this is the analytic space corresponds to a QP t plus minus 1. Okay? Yeah, this is a Tate algebra. Then the corresponding perfectoid cover, which is we call this t tilde 1. So this is an analytic space corresponds to not QP. Okay, for simplicity, we just start from CP, okay, because we need to start from some perfectoid field. So this is CP plus all this p powers roots of t plus 1 minus 1, okay? So this is a perfect algebra. So this is a typical example of perfect algebra. Sorry, I don't have time to introduce the precise definition of perfect algebras. But I think the key point is that we'll go to this perfectoid level. I mean, you have a lot of nice properties about this perfectoid algebra and associated perfectoid space. So you can play a lot of game of it. But unfortunately, you see this ring is too big. It's not another ring. So this means it's not in a tall set of X. Okay? Not in a tall set of this T1, for example. So, but this is the limit of a tall things over T1, right? So, for example, you have this T1M, intermediate objects. So the T1M, just the analytic space associated to this T plus minus 1 over P to the N, okay? Yeah, so each step is finite tall, finite tall, finite tall, and you take a limit. You get this one. Okay, so this is inspired the so-called Pareto side of X. So suppose if X is a rigid analytic variety, say over K, okay? And this Pareto set X. Okay, so it's Pareto set on X. So this is much bigger than this étale set. It contains étale set. So every rigid variety which is étale over X is in this set. But this has more objects like as showed in these examples. So the typical element in this Pareto set is like this: U equal to inverse limit of Ui. Okay, and then each Ui is in a tau set of X. And moreover, as this connecting map becomes, finite tau, eventually, finite tau surjective. So Ui to the Uj, so finite tau surjective. If J is sufficiently large, so eventually it becomes finite tau surjective thing. Okay, so the Pareto set consists of objects like this. Yeah, so see that this one is really in this Pareto set. And this Pareto set also has good property that usually if you want to compute something, for example, local system on a tau set of X, okay, then first pull back to this Pareto set, then compute the cohomology in the Pareto set, get the same thing. Okay? So most of the things you play on the tau side, you can play on the Pareto side and get the same thing. And the key fact, when you use Pareto set, Pareto set is the advantage of Pareto set and the tau set is that, in Pareto set you can really compute the tau cohomology, in a concrete way, okay? Not just by definition, but in the concrete way, you can reduce it to compute some, for example, the coherent cohomology. And the key fact to this calculation, the key fact is like this. So this affinoid, perfect toy space. Form a basis of the Pareto set. Okay, so this is just a affinoid perfect toy space. Affinoid just means, this is a space associated to a single algebra, right? Affinoid perfect toy space. This is one example. Okay, sorry, this one. Yeah. So this means if you want to define something in this site, Pareto site, for example, define sheaf, you just need to associate two sections on each of these affinoid perfectoid. Okay, and check that they satisfy the compatibility condition. They'll automatically get a sheaf. Okay, so let's enable us to really globalize this construction of this BDR. So for example, if R is a perfectoid algebra, say over QP, then you can mimic Fontaine's way to construct this BDR associated to this perfect algebra. Okay? And further globalize, you can glue all of this, you get this so-called deRham sheaf, the deRham period sheaf. Okay? The period sheaf. This sheaf is on the Pareto set. Okay, we can only define the sheaf on the Pareto side. We cannot do it on the tau side. Yeah, the reason is that this kind of thing never lives in this tau side. Okay, so we've done some good work, but however, this period sheaf is useless in most of cases. Yeah, not enough. So why? So let's come back to the classical case. Maybe just right here. So in the classical case, we have p-adic representation of GK. Okay, K is a finite extension of QP. And if this is deRham, then we have this the DDR V tensor over K tensor with BDR isomorphic to V tensor QP BDR. Okay, we have this this is isomorphism. If once V is deRham representation, let's see that it's K. To have this isomorphism, we implicitly have this K is actually embedded in BDR. Okay, as I said earlier, we have QP bar embedded in BDR. Okay, so if we want a similar thing in the relative situation, we should have that. We should have this sheaf is actually a sheaf of OX modules. Okay, we should have this sheaf to be OX module, but it is not. This BDR is not a sheaf of OX modules because this BDR is not a sheaf of OX modules. Okay. Even what? This. Ah, okay. How to from here to here? Even before this. Ah, how to this? Okay, you can just imitate the Fontaine's this functor. So I have this BDR, you have this R, you get this the so-called tilting, which is defined to be the inverse limit of this R, the connecting maps X to XP. Okay, something like this. Then you have this bit vector of this. I think it's better to use. This one is a bound algebra, complete. Okay, this is perfect bound algebra of a characteristic P. Okay, then I'll take the power bounded elements. Okay, this is mapped to. Then if you invert P, then it's mapped to this R. Okay, just like the classical case. So R is CP, then you have this, yeah. Okay, then this is called theta. Then you just define this BDR plus R, the kernel set completion. Same thing, yeah. Completion of. This flat, I mean, here. Kernel set completion of sheaf, yes? Yes, you need to check that. It's not straightforward. You need to check that it's certified.
How do you get gold BDR?
How from here to here? Yeah. Okay, as I said, these things, okay, so this R, okay, this is perfect algebra, give rise to a finite perfect space. And this is the basis, topological basis of the site. Okay, once you have a section on each basis, you check that they satisfy the compatibility condition, is automatically give you a sheaf. Okay? Yeah, this is actual nonsense. I need to check that they satisfy the compatibility condition. So for example, if I have a finite perfectile space, then I have a covered by a finite perfectile space. You need to check that they satisfy the sheaf axioms. Okay? Yeah. This is straightforward things. Sorry? X, which one, sorry? Perfectile algebra and X. X is a rigid analytical variety. Okay, then you can consider the perfectile space over X. Okay, which has a morphism to X. Like in this case. So this is our X. Okay? And this is the perfectile things. These very big things have mapped to X. But this is not in the étale site, it's in the pre-étale site. Yeah. Okay, so here I need to specify what is OX and yeah. Okay, so now I introduce some formal definition. Yeah, so you have this x per état set. It has a natural projection to the état set. Okay, we call this nu. And if x fits into, for example, CP, I consider per état set of XCP. This is naturally unbiased to x per état because XCP is in the x per état. Yeah. To this XCP. Okay. Yeah. So this we call the nu pri. Okay. Then this OX, which is a sheaf on the per état set of x on x per état, is by definition is pullback of structure sheaf on x état. And similarly, I have the sheaf for differentials OX, omega x 1, omega 1 x état. Okay. Okay. Then actually, what we need, the main object to play with is the so-called OBDR. Okay, OBDR. So this is what? This is a sheaf somehow combines the deRham periods and also the structure sheaf. So I won't introduce the definition, but for our purpose, we just know that this is a sheaf of OX modules. Okay, and together with a flat connection. Flat connection. And also we have a filtration on this OBDR together with plus filtration and satisfy this Griffith's transversality. Satisfying transversality. Okay, everything in a geometric setup, once you have flat connection, you always expect it to satisfy the transversality. Okay, this is due to shorts, sorry. Yeah. I should make it, yeah. We introduce the framework, and then we work on this framework. So, yes, I mean, so far this is foundation things like perfect spaces and per état set, and this structure things they all introduced by short. I saw this less well-known thing, so I didn't say. Just means a few I. It contains a few I minus I. Yeah, the standard. OBDR what? Okay, yeah. Bruno, yes. Yeah, the local piece, I mean, locally, if, for example, on here, I mean, this OBDR is already constructed by Bohino in his thesis. Yeah. Okay, now we go back to our local system L. We pull back it to the per état side. Okay, then okay, then define this DDR I L, defined to be the push forward of L tensor with this tensor with this OBDR. The tensor with, okay, oh sorry, I forgot to say what is a deRham local system. So here, so L, for example, a local is called deRham. If so there exists a coherent, vector bundle say M on X et al. With a flat connection. Such that L tensor with this OBDR. Okay, it just means we pull back this L to pre-tau side first. So this is, you can either write L or L hat, doesn't matter. It's isomorphic to this M tensor with this OBDR. Okay, this tensor is over OX et al. Or over OX. If you pull back M to the pre-tau side, then you over OX. Okay, with respect to the connection, okay? Yeah, because both sides has connection. This has connection, the tensor plot connection. This connection is trivial thing. Okay, so I should say that, in p-adic Hodge theory, we always expect to have something similar to classical Hodge theory, for example, the matrix. But so far, we don't have yet. This is our dream. Okay, so at this moment, we don't have matrix and so on things. But you need a matrix to define a connection. I see. Yes, we have connection, but this connection somehow is do by hand. We don't have metric at this moment. Yeah. Sorry? Yeah, I will say a little bit more about this. Yeah. Okay, then we define this. Yeah. Okay, so this is somehow just like the relative, analog of this DDR things. But now we have higher images, not just sorry. In fact, we also have higher images in the classical case, right? The taking invariance also have H1 things. Okay, so this is exactly just a geometric analog of the classical case. And the result is similar. Result is similar. Okay, so first, whatever L is always a vector bundle. It's a vector bundle. Okay, plus a flat connection and a plus transversality. Okay, maybe it's a filtered vector bundle. Transversality. And vanish if I is bigger or equal to 2. So this means we have DDR0 and DDR1. This is exactly the same as the classical case, so H0 and H1. And also, this DDR0 is isomorphic to DDR1. Okay, this is also the same as the classical situation. And to prove the main result, the deRham rigidity, we have the following phase change problem. So this is a pretty strong property. any f. Okay, so here I need to assume that x is smooth. Sorry about that, I smooth. Rigid variety. It's a morphism of smooth variety, rigid varieties. Okay. Then I have this. This is a functor DDR. DDRI commute with this pullback. Commute with this f. Okay, you see that from here we can conclude the deRham rigidity because first we have the global DDR is vector bundle. Then we know at one point it is of the expected dimension. Okay, this is deRham. Okay, this means the vector bundle itself is of the expected rank. Okay, but it's you just take y to be that point. Okay, then you can conclude that this vector bundle always have this expected rank. The rank is the same as the rank of the dimension of the local system. Of course, then we need to do more work to check that this DDR0 satisfies this isomorphism. Didn't work. Yeah, so that is what I say. If x naught is drawn for some x naught, then L itself is drawn. Yeah. All right. So then to prove this, so we call this a p-adic arithmetic Riemann-Hilbert correspondence. And actually, we also have a geometric Riemann-Hilbert correspondence. It's something like this. Yes, yes, yes. Because this ring is not defined in the top side. Yeah, that's the point. Yeah. Sorry? Yes, for example, I mean, once someday we have, for example, concept of perverse sheaf, something you can definitely apply. Yeah. So I think I don't have time to speak about this p-adic geometric things and the symmetry correspondence. Maybe just talk about the p-adic symmetry correspondence. Okay, let's go back to this situation. So, so this x pretty tall. Yeah, so we have this community. Oh, I just erased it, so I shouldn't. Anyway. Yeah. And to this XCP, okay, to this. Okay, this is called new, this is called new prime. Okay? So then if we have this the thing as L tensor with OBDR, you push forward to X at all. Then you can actually first restrict on this XCP pre at all, then push forward to XCP at all, then push forward to X at all. Okay? Then if we focus on this step, then we realize that, I mean, at some point we realize that this recovers the p-adic symmetry correspondence. So, okay, I'll write down the exact formulation. Okay, so we define this OC to be the growth zero of this OBDR. So this growth, as I said, this OBDR also has a filtration. Okay, I'll take this growth zero of the OBDR. Now, if we, because this connection satisfies this transversality, you can take a grid piece of growth zero of this theta, this nebula. They'll get a theta. Nebula is a connection, and theta becomes a Higgs field. This is a key observation. OC. So it's omega 191. Okay, you have a twist. And this is a Higgs field. Okay. So now we define this HL. L hat tensor with this OC. And pushing forward. So R star prime. Okay? So push forward to this XCP. So actually, the CP can be replaced by any perfectoid field which contains all p powers roots of unity. Okay? Yeah. We just take a CP to be a simple example. Yeah. Okay. Then this is a module on this side, and with a Higgs structure. Okay? Yeah. This has a Higgs structure. The main result is, for this part is, first, this is a push forward. This is a derived push forward. And the first result is that the higher direct images vanish. So this means HL just isomorphic to, just equal to the push forward. And it's always have the expected rank. The rank of this this vector bundle is same as the dimension of L. Okay, so this is a Higgs bundle. So it's a tensor functor. QP from QP local systems on the étale set of X to the Higgs bundles. On this XCPA. Yeah, actually, this is a new potent. Higgs bundles. And with semi-linear allo action, GK action. Yeah. And they satisfy the Birch property. And also, we have the pushing forward property. So F is proper smooth. If F is proper smooth, I think from XY, I consider the higher images of this Ri at lower star of L. Okay. So recently, Candela and me, we proved that this is always a local system. If we start from a local system on étale side of X, you'll take a higher push forward. You always get a étale local system on Y. Okay, this is not known for rigid varieties before. We just recently proved that. Then can we apply this seamless correspondence, this functor is isomorphic to the R F X over star. I'll finish just with one example, just 1 minute, then we finish. So you see that this H things is kind of graded modules over this DDR things. So if we can prove this, we can prove that. Okay, so the key thing is to prove this. Yeah. And to prove this, we use some foundational work developed by Kira and me on the relative figure modules. Yeah, we reduce it to some very explicit calculation and so on. I don't have time to talk about that, but just show you one example, then we finish. The example is to give you the definition of this. What is the Higgs push forward? L, just take it to be the trivial local system QP. Okay, then this HL, because this is a trivial local system, and this function is a tensor function, so this is rank 1, and also nilpotent, so it has to be trivial Higgs bundle. Okay, so this has a trivial Higgs field structure. Okay, then we apply this push forward property. What do we have? So left-hand side, if you apply this, you just get actually in a situation for classical sign theory. So actually you get, what you get is, 3 implies. So left-hand side is just equal to, sorry, I forgot to give the definition. All right. So this definition is that you consider this deRham complex for this Higgs field. So this is HL to this HL, tensor with omega 1, x over y, is by -1 to this HL, x over y, to -2, and so on. Okay, you have the deRham complex for the Higgs field, then you push forward. Okay, so this is the definition of this. Now we apply this to this trivial local system. We get the left-hand side is just equal to HI SQP, you base change to CP. Okay? And the right-hand side, you see that because, sorry? Oh, yes. Yes. Yeah. On the right-hand side, because this Higgs field has a trivial fixed structure, so this means this is the theta map. Okay, all of this theta map is 0 map. Okay, it's a trivial map. So the connecting map is 0. So if you compute push forward, the spectral sequence just degenerate at the first term. Now you see the right-hand side is exactly what we have at the beginning of the talk. Okay? Yeah, this is exactly yes. Okay, I think I shouldn't write like this. Okay? And this recovers this is equivalent recovers this Hodge-Tate comparison theorem. Okay, but we have a different point of view. Now we use Higgs field to recover this Hodge-Tate comparison. Okay, I think I already out of time for 5 minutes. Sorry about that. I'll stop here. Okay, that's a very good question. So, yeah, we have some work in progress concerning the Shimura variety application. So, so see that our theorem is that I mean, basically on the rigid analytic world. So this means we apply the result to Shimura varieties. So first, take the rigid identification with Shimura varieties. Then you can show that the local system is deRham. You get DDR things. But this is only a vector bundle on the rigid identification. Okay, so now we have work in progress that we have a log variant of this construction. So this means, if you have projected smooth things and with normal crossing divisor, okay, then you may consider the cumulative set of this complement. Okay, that can prove that in this situation, we start from a local system, on X. Okay, then we can prove that finally you also get a vector bundle with flat connection, but with log poles on this D. Okay, in particular, show that this vector bundle is algebraic. Okay, this is somehow the work in progress. And you can also compare this deRham periods, because now we already proved this is algebraic. So we can compare it with a complex period. Okay? Because we expect the Shimura to be motive. Of course, we cannot prove it to be motive. We cannot prove it is really a motive at this moment, but you should have the similar properties with motive, and I want to verify that. So this is work in progress. Okay. Yeah, for compact things, it's automatically. Yeah, I think I expect so. So you can, somebody, I know somebody, they use the Higgs bundle on the compact situation to really do some classical things like Shimura, like you said. But I don't know much about detail. Yeah.
So when you say recovers Hodge-Tate comparison,
yes.
Does it also recover Falting's theorem?
Oh, what thing?
Falting's. Does it recover Falting's?
Okay. Recover the Falting's comparison theorem. Yes, but with completely different approach.
Okay.
Yes.
And then second question is, what happens if you just use the usual Leray spectral sequence for base change?
What do you mean, Euler spectral sequence for base change?
You have a change of site, right?
Change of site. Yes.
Yeah. So there's the classical Leray spectral.
Yes.
What happens if you play around with that?
Yes, that's a good question. So, okay. So, the key point is that in a Pareto site, okay, so you have this, for example, something like X, okay, this we are interested. There have something, for example, the X-tude, okay. Locally, we can always construct a Pareto cover, like in the example. So, yeah, so this is like T-tude one, okay. Then what we want to compute is something like this, okay, on the Pareto site. Then by definition, this thing is what? Is that for any like y, which is in the Etal set of X, okay? So you can put back everything on the y Pareto, right? Then compute this push forward. Then they'll shiftify this pre-shift, right? By definition, it's like this. Okay, then we prove that this is really a coherent shift. So to prove that this satisfies the base change property, if for y, which is in the Etal set of X, okay? And to show that, our strategy is that it's very good to compute Pareto site because you have this kind of thing. So in this kind of thing, you always have that if I have vector bundle, it hierarchical module vanish, okay? And this is like a Galois cover. This case is I think, the Galois group is ZP. Okay, then to prove the cohomology of X, of something on X in the site, you just need to write down sections on here and compute the Galois cohomology. Okay? Yeah, this is the basic strategy. And for Galois cohomology, it's very easy to control things. But everything is to use this relative figure modules. So you transfer this Etal site to somehow, this figure modules and compute on the framework of figure modules and something like this. Okay. So this is the strategy of the work.